Hello friends, welcome to my channel. Today I would like to help you with the topic atoms, molecules and stoichiometry. At first, let's see relative masses of atoms and molecules, some important definitions. Atomic mass unit or unified atomic mass unit is defined as 1/12 of the mass of a carbon-12 atom, and we use the symbol U, and it has a value of 1.66 times 10 to the power minus 27 kilogram. This is the definition of relative atomic mass. Symbol is AR. This is weighted average mass of atoms in a given sample of an element compared to the value of the unified atomic mass unit. Relative isotopic mass is the mass of a particular atom of an isotope compared to the value of the unified atomic mass unit. Relative molecular mass MR is the weighted average mass of a molecule in a given sample of that molecule compared to the value of the unified atomic mass unit. We can find the relative molecular mass MR by adding up the relative atomic masses of all the atoms present in one molecule. Here is an example. Methane is CH4. AR values of carbon is given here, and hydrogen is also given in the periodic table. So take the values from the periodic table and then substitute that for AR values, and since there are 4 hydrogen, multiply by 4. 1 times carbon plus 4 times hydrogen gives you the MR of methane. 12 plus 4 equals 16. The next is relative formula mass MR. This is the weighted average mass of one formula unit compared to the value of the unified atomic mass unit. As you can see here, we use the term formula mass always for an ionic compound if there are ions. For example, magnesium hydroxide, it has got magnesium ion and hydroxide ion. So take it and add all of those to get the mass MR, molecular mass or relative formula mass. What do you mean by water of crystallization? Some compounds can form crystals which have water as part of their structure. This water is called the water of crystallization. So what will be anhydrous compound that does not contain water of crystallization is called an anhydrous compound. Example, anhydrous copper 2 sulfate CuSO4. Hydrated compounds contains water of crystallization. Example, hydrated copper 2 sulfate, copper sulfate CuSO4.5H2O. That 5H2O indicates the water of crystallization. Accurate relative atomic masses. A mass spectrometer can be used to measure the mass of each isotope present in an element. It also compares how much of each isotope is present. The relative abundance. That's called relative isotopic abundance. And this is a diagram of a mass spectrometer, simplified version. As you can see here, vaporized sample is passed through the spectrometer. There will be positively charged electrodes, and heated filament produces high energy electrons. Ionization chamber is there, and you can see the ion detector and a magnetic field. So positively charged electrodes accelerate positive ions, and this detector detects the ions, records, and we get a spectrum. We can use this data obtained from here to calculate the relative atomic mass of an element very accurately. The method you have to follow is multiply each mass by its abundance and then add it, divide by 100. So here is the spectrum, type of spectrum you get from the output of the mass spectrometer. The mass spectrum produced shows the relative abundance on the vertical axis and the mass to ion charge ratio on the horizontal axis. The mass spectrum of neon has 3 peaks. Neon abundance 90.9, which is neon 20, and neon 21 0.3%, neon 22 8.8%. So the percentage abundance is given there, the mass number is also given there. So you multiply the mass number with the relative abundance and then take the sum of all those things, divide by 100, gives you the AR, relative atomic mass of neon. So the spectrum helps us to calculate the relative atomic masses. This is an example of neon. If there are diatomic elements, the spectrum looks like this. For example, this is a spectrum of chlorine molecule. So when chlorine is ionized during mass spectrometry, a molecular ion is formed, Cl2+. As this ion is quite unstable, fragmentation may occur, forming Cl and Cl+. The Cl atom isn't detected by the mass spectrometer, but Cl2+ and Cl+ are detected. There are two isotopes of chlorine, so chlorine molecular ion may contain Cl35, Cl37 or both. The mass spectrum will appear like this. As you can see here, the Cl35 is here, Cl37 is here, and then the mass of the molecule 70 is of 2 Cl35 atoms, 72 is of Cl35 and Cl37, and 74 is of 2 Cl37. So that's the output you get for diatomic elements. Next, let's see chemical formulae and chemical equations. Ionic compounds are formed from a metal and a non-metal bonded together. Ionic compounds are electrically neutral. The positive charges equal the negative charges. Charges on positive ions. All metals form positive ions. There are some non-metal positive ions, those are ammonium and hydrogen ion. The metals in group 1, group 2 and group 13 have a charge of +1, +2 and +3 respectively. The charge on the ions of the transition elements vary. That's why we use Roman numerals to indicate their charge. Roman numerals used in some compounds from transition elements to show the charge of metal ions. Charge is otherwise called oxidation number or oxidation state. For example, in copper 2 oxide, copper is a transition element. It has a charge of +2. That's why the 2 is shown in Roman numeral. In copper 3 nitrate, the 3 indicates the oxidation number of copper in copper nitrate. What about non-metal ions? The non-metals in group 15 to 17 have a negative charge and have the suffix IDE. Example, nitride, chloride, bromide, iodide. Elements in group 17 gain 1 electron, so it has 1- charge. For example, bromide. Elements in group 16 gains 2 electrons, so it has 2 negative charge. Example, O2- oxide. Similarly, for group 15, 3- charge, example N3-. There are more complex negative ions, which are negative ions made of more than one type of atom. So we can see the charges of those also. This is the list of common ions and their charges for polyatomic ions or complex ions. This has ammonium NH4+, carbonate CO3 2-, sulfate SO4 2-, phosphate PO4 3-, nitrate NO3-, hydroxide OH-. Other ions: silver Ag+, zinc Zn2+, iron 2 Fe2+, iron 3 Fe3+, copper 2 SiO2+. So this is some of the examples of common ions and their charges. So how to write the name and how to identify. Example, chromium 3 chloride means that there are chromium 3+ ion and Cl- ions. So to balance the charges, then you need to have 3 chloride ions. So formula will be CrCl3. Potassium sulfate is K+ and sulfate SO4 2-. To balance the charges, it needs 2 potassium ions. So the formula becomes K2SO4. Iron 3 oxide, Fe3+ and O2-. In order to balance, there should be 2 iron 3+ ions and 3 O2 minus ions. Therefore, it becomes 6 plus charge, 6 negative charges. Then formula becomes Fe2O3. How to balance equations. You write the formulae of the reactants and products, count the number of atoms of each reactant and product, then balance the atoms one at a time until all the atoms are balanced. Use appropriate state symbols in the equation. The physical state of reactants and products in a chemical reaction is specified by using state symbols. Solid, we use S, L for liquid, G for gas, AQ for aqueous. This is an example how to write balanced equation. A word equation is given to you. Sodium carbonate plus hydrochloric acid gives sodium chloride plus carbon dioxide plus water. If you convert those to symbols, Na2CO3 plus HCl gives NaCl plus CO2 plus H2O. The balanced equation, there is HCl which is not balanced before, so hydrogen you can balance it now. It becomes Na2CO3 plus 2HCl gives 2NaCl plus CO2 plus H2O. That's how you balance the chemical equation. What are ionic equations? In aqueous solutions, ionic compounds dissociate into their ions. The ions that do not take part in the reaction are called spectator ions. An ionic equation shows only the ions or other particles taking part in a reaction without showing the spectator ions. So during the reaction, spectator ions gets cancelled. Only the real ions which takes part in the reaction will be there finally. Let's see an ionic equation. Magnesium plus copper sulfate gives magnesium sulfate plus copper. As you can see here, magnesium and copper are solids. The other compound, copper sulfate and magnesium sulfate, are aqueous, so it dissociates into its ions, forming copper 2 plus and SO4 2 minus and Mg2 plus SO4 2 minus. As you can see from both sides, SO4 2 minus is present in both the sides and they are called spectator ions, so they get cancelled. So while writing the final ionic equation, there is no need to include SO4 2 minus ions. You write only the other species present in the equation, which is magnesium plus copper 2 plus gives magnesium 2 plus plus copper. Do not forget to put the state symbols. The next one is empirical and molecular formulae. Empirical formula, the simplest whole number ratio of atoms of each element in a compound. Molecular formula is the actual number of atoms of each element in a compound. How to calculate empirical formula from masses? Divide the mass or percentage by mass of each element by its molar mass to calculate the molar ratio. After that, divide each number in the ratio by the smallest number to get the simplest ratio of elements. And the last step is, if the ratio contains decimal numbers, multiply it as appropriate to obtain whole numbers. So finally you need the whole numbers, so make it a whole number by multiplying. Example is provided here. It was found that 0.39 gram of carbon was combined with 4.61 gram of chlorine. Calculate the empirical formula of the compound. Atomic masses is provided here, carbon 12 and chlorine 35.5. So at first you divide the reacting masses by its atomic mass values. For example, carbon 0.39 divided by 12. Similarly, chlorine 4.61 divided by 35.5. There you get some decimal values. So the next step is to make them whole number. For that, first divide by the least number as possible, least among those, which is 0.0325. So divide both the decimals by 0.0325 in order to get the whole number. Here you got the whole number ratio as 1:4. So carbon is 1 and chlorine is 4. Thus you get the empirical formula as CCl4. It's actually called tetrachloromethane. If there is combustion data, how to find empirical formula? If the compound contains only carbon and hydrogen, divide the mass of carbon dioxide produced during combustion by 44 to find the number of moles of carbon dioxide. This is equal to the amount of carbon in the compound. Divide the mass of water produced during combustion by 18 to find the number of moles of water. 1 mole of water contains 2 moles of hydrogen atoms, so double the number of moles of water to find the number of moles of hydrogen in the compound. The last step, divide the number of moles of hydrogen and carbon by the smallest value to find the simplest molar ratio. This is the empirical formula. Example: a sample is burnt in oxygen, 0.069 of carbon dioxide and 0.0113 gram of water is produced. What is the empirical formula of the sample burnt? First of all, moles of carbon in the sample equals mass over molar mass, 0.069 over 44 equals 0.00157. The next thing is about water, 0.0113 over 18, but as you know, one water contains 2 hydrogen, so doubles it, multiply by 2 to give the moles of hydrogen, and then divide by the least number, so it becomes 1.25:1. Empirical formula ratio, you make it as a whole number by multiplying any number by multiplying these two numbers by 4. So when you multiply, you get 5:4. So your formula is C5H4. Empirical formula. If the compound contains other elements as well as carbon and hydrogen, the steps to be followed are: use the mass of carbon dioxide to calculate the number of moles of carbon atoms, then use it to calculate the mass of carbon present. Second step, use the mass of water to calculate number of moles of hydrogen atoms. Then use this to calculate the mass of hydrogen present. Add the masses of carbon and hydrogen and compare to the initial mass of the compound. If there is no difference, the compound is a hydrocarbon. So continue with step 4. If there is a difference, assume that this is due to hydrogen. Calculate the mass of oxygen present and use this to calculate the number of moles of oxygen atoms. Fourth step, divide the moles of each element by the smallest value to obtain the empirical formula. How to calculate molecular formulae? Calculate the relative formula mass of the empirical formula, then divide the relative formula mass of the compound by this calculated value. This will show how many times larger the molecular formula is than the empirical formula. Here is one example. A compound has the empirical formula HO and the relative formula mass is 34. What is the molecular formula? Empirical formula mass equals 16 plus 1. Oxygen is 16, hydrogen is 1, so you get 17, and the formula mass is 34. So your how to calculate is you divide 34 by 17. You will get a number 2. That means you multiply the empirical formula by that 2. So HO becomes H2O2, which is called the molecular formula of that particular compound. The next section is the mole and the Avogadro constant. The number of particles equivalent to the relative atomic mass or relative molecular mass of a substance in grams is called the Avogadro constant or Avogadro's number. The symbol for the Avogadro constant is L. The symbol Na may also be used. The numerical value of Avogadro constant is 6.02 times 10 to the power 23. The mass of a substance with this number of particles is called a mole. How do you define a mole? It is the amount of substance which contains Avogadro number of specified particles, and the particles can be atoms, molecules, ions, or electrons. 1 mole of any element is equal to the relative atomic mass of that element in grams. 1 mole of carbon, that is, if you had 6.02 times 10 to the power 23 atoms of carbon in your hand, would have a mass of 12 gram. 1 mole of water would have a mass of 18 gram. Reacting masses and volumes of solutions in gases. When completing calculations in chemistry, quantities should be given to the same number of significant figures as the least accurate measured quantity. So if the values are given to 2 significant figures, then the answer should also be given to 2 significant figures. We are going to calculate which involves the reacting masses. Molar mass is the mass per mole of a substance and can be calculated by adding the relative atomic masses of all the atoms in the formula. To calculate the number of moles using mass and molar mass, we use this formula: number of moles equals mass in grams divided by molar mass. And if there is volume, at the same temperature and pressure, 1 mole of any gas will occupy the same volume. At room temperature and pressure, this is 24 dm cube. This does not mean that these gases will have the same mass. The number of moles of a gas at room temperature and pressure can be calculated, where V is the volume. Moles of gas equals volume in dm cube divided by 24. And if there is concentrations involved, concentration is the amount of solute dissolved in a given volume of solution. The number of moles can be calculated from concentration and volume. Concentration in mole per dm cube and volume in dm cube. Number of moles equals concentration times volume. So these are the points to be noted in this topic. That's all. Thank you so much for watching this video.